This is our Albatross subscale, currently sitting in its transport configuration on our representative trailer. So we're going to show you moving from transport configuration to flight configuration. So all that takes is taking each wing, unfolding, and then twisting our locking pin into place to lock the rotation of the wing, and then doing the same for the aft wing. So this wing folding is representative of the full scale in terms of its span location, as well as the general wing folding strategy and folded locations as well.
This is the ground control station, or the GCS, which we use to control the vehicle in the field. In the lab, the GCS doubles up as a flight simulator, which allows us to test out our control laws, maneuvers, and refine them as required before we perform them in the field. The Albatross is designed for simplified vehicle operations, or SVO, which involves the holistic design of inceptors, flight control laws, and displays to significantly reduce pilot workload and allow safe, proficient operation of the aircraft, even by a minimally trained operator. The VSDDL SVO implementation, refined through prior FAA-funded research, has been successfully flight tested on multiple different subscale VTOL configurations. At its core is the patent-pending Trajectory Control System, or TCS, which provides coordinated control of thrust, wing tilt angle, and pitch attitude to achieve the pilot's trajectory commands. For manual flying, the pilot's inputs to the flight control system are through a right-hand inceptor, a left-hand inceptor, and pedals. I pull on the right-hand inceptor and the aircraft climbs. To descend, I push forward on the right-hand inceptor. So if I displace the right-hand inceptor to the left, the aircraft banks left. And if I displace it to the right, the aircraft banks right. I push on the right pedal in order to yaw nose right, and on the left pedal to yaw nose left. To accelerate forward, I push the left-hand inceptor forward, and as you can see, the aircraft starts accelerating and picking up speed. To decelerate, I pull aft. These are the displays that are available to the pilot and the flight test engineer in the GCS. So we have a status display that shows us whether the vehicle is armed or not, whether the ground control station has control, and a flight timer. We also have an indication of what control laws are effective, so whether it's the trajectory control system or any other control scheme, whether the operation mode is vertical takeoff and landing or conventional takeoff and landing, if the vehicle is so equipped, and whether or not changes between vertical, hybrid, transition, and forward flight modes are enabled or locked. We also have a battery indicator, which is not connected. We have a wing position indicator that shows the position of the wings on the aircraft. Here we have a map of the flight test arena at Sharp Field, along with a grid where we've defined coordinates for autonomous navigation. This is the primary flight display for the pilot, so it shows the states of the aircraft, altitude, airspeed, vertical velocity, heading, flight path angle, and so on. Up here is the connection status display for the flight test engineer, which shows whether the aircraft is in proper communication with the ground control station. And below here is a display for the flight control system intermediate commands, so we can see all the commands that are generated by the middle loop and the inner loop of the flight control system. To help the pilot in manual flying, we have a number of holds that are available as part of our SVO philosophy, and these holds go into engagement without the pilot having to actively engage them. So here you see the aircraft is in hover, and it's got heading hold engaged, it's got an altitude hold engaged, and it's got position hold engaged. If the pilot displaces the right-hand inceptor to climb or descend, that breaks the altitude hold. If the pilot then recenters the inceptor, the aircraft levels off and altitude hold is established at the new altitude. If the pilot uses the pedals to change the heading of the aircraft, that breaks the heading hold. Once the pilot removes the pedal input, the heading hold is reestablished at the new heading. If the pilot moves fore aft or left-right, that then breaks the position hold. If the pilot then centers their inceptors, the aircraft comes to a hover, and that reestablishes the position hold. The yellow dot is the anchor point that the aircraft is going to track, and that shows you how far away the aircraft is from the anchor point that has been established. Over here, we have the auto flight panel with a number of automatic flight functions to help the pilot. The auto takeoff function, if engaged, causes the aircraft to take off vertically and then level off at a programmed altitude, in this case 15 feet. The auto land button does the reverse. It brings the aircraft down to a gentle landing at a pre-programmed descent rate. DXN stands for departure transition, and its role is to accelerate the aircraft from hover to forward flight. So if I engage DXN, as you can see, the speed command increases to 44 knots. The aircraft begins to accelerate. The wing starts coming forward. As you can see, the aircraft's accelerating, and it will accelerate through hybrid flight mode, then reach transition flight mode, and then finally forward flight mode with the wing in fully forward position. So the aircraft now is flying like an airplane. AXN stands for arrival transition, and its role is just the opposite: decelerate the aircraft from forward flight to a hover condition. So if I press AXN, the speed command drops to 0, the aircraft begins to decelerate, enters back into transition flight mode, and then into hybrid flight mode with the wing moving towards its vertical position. And as you can see, the aircraft decelerates and will ultimately come to a hover with all holds engaged. So here you see altitude hold, heading hold, and as the aircraft comes close to hover, the position hold also gets engaged. CTL stands for centerline track, and if engaged, the aircraft tracks along the runway centerline at sharp field. Circ stands for circle, and as the name implies, it allows the pilot to put the aircraft into a bank and then engage circ, which then causes the aircraft to maintain a constant radius circle while compensating against wind. Return, if engaged, causes the aircraft to return back to the takeoff site along a specified route. The return mission also gets engaged automatically if there's a communication breakdown between the GCS and the aircraft. PROG stands for Program Maneuvers, and it allows the pilot to engage a program maneuver from a set of program maneuvers, and these could be used for performing system identification or performing other maneuvers or sequences of maneuvers to characterize the flight performance of the aircraft. The aircraft is capable of autonomous navigation from takeoff to landing, and this is engaged by pressing the nav switch. So now I'm being prompted to select from one of 5 possible missions. Let's say I select mission M1. I'm now prompted to engage the mission, and now the aircraft will take off and then start navigating along a set of waypoints, whatever waypoints have been programmed. And we actually demonstrated this in flight when we were flight testing the aircraft. The first day that we're flight testing this aircraft, so we're keeping everything nice and slow, relatively low altitude, relatively low airspeed.
This is our prop motor thrust testing setup, which has a load cell in it to measure the thrust. So as you can see here, the motor and the prop and the battery over here is used, which is actually used in our subscale aircraft. So the prop gets rotated this way, and then the load cells measure the thrust, and this the data that we get from this experiment can also be used, or is also used, to get a PWM RPM mapping, which is then used in our simulation model and actually when flying the aircraft. So we have inverse propulsor model, also called IPPM, that we use in our simulation model, and also is used while actually flying the aircraft. So IPPM is generated by using the manufacturer performance data. We normally use APC props. So the propeller performance data is then used, the thrust for different advanced ratio and RPM is used to create an inverse propulsor model, which is used in our control system.
Here are the experimental setups for measuring the moments of inertia of our as-built vehicle. You can see the aircraft oscillating about the roll axis on the left, the pitch axis in the middle, and the yaw axis on the right. The angular motion is recorded by avionics on the rig, sent as telemetry and post-processed to determine the average period of oscillation from multiple runs per each axis. These periods are then used to calculate the inertia values, which are then fed into our simulation model.